Hello and welcome to this video where today we're going to be looking at the strong nuclear force. Now we know that there are four fundamental forces. We've got gravity, the electromagnetic force, the strong nuclear force and the weak nuclear force. Now two of those forces obviously we're very familiar with, so gravity obviously we're familiar with, and also the electromagnetic force or the electrostatic interaction we're also very familiar with. And they're things that we see around us all the time. But this strong nuclear force must also exist, because if it didn't, if we only knew about, for example, gravity and the electrostatic force, and they were the only ones that existed, then the nuclei in atoms wouldn't be able to exist. So if we take this nucleus, for example, it's made up of our protons, which are these ones, and neutrons, which are these ones. If we only had gravity and the electromagnetic interaction, this nucleus would basically just fall to bits. Gravity isn't strong enough to keep all of these things together, because the electromagnetic force would basically repel all of these protons away from each other, and so this thing wouldn't stay together. So there must be something holding it together, and that's where this strong nuclear force comes in. So it's called a strong nuclear force because it must be stronger than the electromagnetic force, because if it wasn't, the electromagnetic force would overcome the strong nuclear force and this nucleus would still fall apart. Now we've seen that forces are mediated or carried by different particles, and for the strong nuclear force it depends what we're really looking at. So if we're looking at particles that are made up of quarks, so for example our mesons or our baryons, then in this case pions are the particle that mediate the force between hadrons. So for example, between these two particles here, between these two protons, they're exchanging some pions, which themselves are made of quarks. So these pions are constantly going backwards and forwards, and these are the things that mediate this particular force. However, if we look at inside these nucleons in this case, so here we've got a neutron, and it's made of two down quarks and an up quark, as we saw again in the previous video. Now this thing, in this case, this doesn't use pions to actually mediate the force between these three quarks. Instead, there's another new particle, and these new particles that are constantly swapped over between these three quarks in this case are called gluons. And they're called gluons because basically they glue these three particles together. So we say that the gluons mediate the force between these quarks. Now, in terms of your exam, basically the only thing that you really need to know for the exam is that the pions mediate the force between hadrons. That's basically what all of the textbooks say. But it's probably a good thing to know that gluons are actually the real basic things that actually mediate the force in terms of the strong nuclear force. But really, if you're asked, pions are the things that do it. So we're going to look at the strong nuclear force in a little bit more detail. So here what we've got is we've got two neutrons, and what we're going to do is we're going to look at how the force between these neutrons varies as we move them together. So here we've got two neutrons far apart, and then we've moved them closer together, and then they're even closer together. And we're going to draw a graph to show how the force varies with this separation, in other words the distance between these two things. Now this graph has got a couple of bits that we need to have a look at before we can actually plot this graph. The first thing we're looking at is the separation. So the scale for this axis is given in femtometers. Now femto basically means 10 to the minus 15 meters. So that's the first thing. We're looking at incredibly small distances from about 5 femtometers downwards. And the second thing is we're going to split this graph into two. So wherever we've got a repulsive force, we're going to say that the force is positive, so it's going to have a plus sign in front of the values. And wherever it's an attractive force, it has a minus sign. So we can distinguish between repulsive forces and attractive forces simply by the sign of the actual force that we're looking at. So for example, here we've got a force of minus 20 kilonewtons at this point here. And because it's minus, it's attractive, and the size of the force is 20 kilonewtons between these two things. If we have a look up here, we've got plus 20 kilonewtons, so now we've got a repulsive force, so these things are pushing each other apart, but again with a force of 20 kilonewtons. So the sign tells us in which direction the force is acting, whether it's attractive or it's repulsive. So when we're a long way away like this and the neutrons are a big distance away, then we're kind of out here and they feel no force between them, at least in terms of the strong nuclear force. So basically out here they'll just sit still. If we move them in a little bit though, then the separation decreases, and so we move to about here. And when they get within sort of like 5 to 4 femtometers, then they start to feel the force of attraction, and so these two neutrons will attract each other in, so they'll both feel a force and they'll start moving towards each other. And as they do so, the separation will go down because they get closer together, and the force increases. And the force increases up to a really, really big number. So we're looking at greater than 20 kilonewtons. So here, these two things would accelerate towards each other incredibly quickly when we get to these sorts of separations. As they get closer together though, the force then becomes smaller until eventually the force becomes zero. So we end up with these two neutrons here, and they're sat here, and the force on them is zero. So here they're in equilibrium, where the force is equal to zero. So basically they would now just sit here, and they're quite happy just sitting there. If you pull them further apart, then you'd pull them further apart, and they'd feel a force of attraction again, and they'd go back to this point here. If you then push them together, so you make the separation even smaller, then we must again move in this direction because the separation is getting smaller. And in this case then, the force then becomes repulsive, and they don't want to be this close. They want to move they kind of want to move away from each other back to their equilibrium position. So there'll be a force acting in this direction now, and so they'll want to basically the force at this point is zero. So they want to basically go back to this point here. So this graph is, you basically need to learn this graph. So this is what the specification says. It basically says that you need to know about the strong nuclear force. Well, that's what we're talking about. Its role in keeping the nucleus stable, which we'll have a look in a second, but this bit in particular. So we've got short range attraction to about 3 femtometers. In other words, there is an attractive force up to about 3 femtometers or so. So here. And that you've got short range repulsion below about 0.5 femtometers, so here. So basically what they're really saying is that you need to learn this graph, and you have to be able to state these numbers. So these are the numbers that really you need to learn. So we're going to have a look at this now. We're going to have a look at how the nuclear force keeps these things stable, and what happens if the nucleus becomes unstable. So here we've got a nucleus, and it's got obviously our protons and neutrons in it, and at the moment the strong nuclear force is keeping this nucleus stable. It's keeping it together. But what we saw in the previous slide was that the range of the strong nuclear force only goes up to about 3 or 4 femtometers, which is basically the same as the diameter of one of these protons or neutrons. So really what that's really saying is that this neutron, for example, can only really attract this neutron and this proton here. It can't interact with anything further away because the strong nuclear force has such a short range that it can't attract this one, this one, this one, and this one. So really, this neutron can only keep this part of the nucleus together, and likewise, this proton can only keep these parts of the nucleus together. So if you then don't end up having a really big nucleus, so let's imagine that we now take some more of these things and we put some more neutrons in like this. So we're making and we put some more protons in, and so we're making our nucleus even bigger. Then we start to end up with an unstable nucleus, because basically what's happening is these parts can stay together and these parts can stay together, but now because we've added more protons, the size of the electromagnetic force has also got bigger. Now the electromagnetic force, if you remember, has got an infinite range. So although the strong force is keeping these parts together really strongly, this proton here is being repelled not only by these ones, but also by all of these out here. So the bigger your nucleus gets, the more unstable it gets, until what happens is the nucleus becomes so unstable that it can't hold itself together anymore. So basically what happens is it kind of falls to bits. So it kind of emits a particle or a group of particles, and the particles it emits are 2 protons and 2 neutrons, and this is what you learned at GCSE, because this is your alpha particle, and this is the reason that alpha decay happens. Basically the nucleus of this atom couldn't hold itself together anymore, because in the end the electromagnetic interaction became stronger than the strong interaction, simply because the strong interaction works over such small distances, and so in order to make this thing more stable, it got rid of some of the protons and neutrons, and so it got rid of this. So then you can do what you did at GCSE. So you can, for example, look at alpha decay. So here we've got uranium. It's got 92 protons. It's got 238 protons and neutrons. It decays to thorium and an alpha particle like this. Right. So just like at GCSE, these two numbers, the 2 protons and the 2 protons and neutrons, these two numbers you have to remember. So you're not told it, you won't be told these in an exam question, but what you could be asked to do is to basically complete this equation. So you'd have to add these numbers in and then complete these numbers here. So just like you saw at GCSE, however many protons and neutrons you start with, you have to finish with. So we started off with 238, 4 are here, so we'd have 234 there. And here we've got 92 protons, 2 of them are here, so therefore we've got 90 protons there. But I can't stress enough, these two numbers you must remember. So remember these, because if you don't remember these, then you won't be able to answer these equations. You won't be able to answer these types of questions where you have to complete these equations. Now, there's a little bit more information that we can then take from this strong nuclear force. So we've seen in previous videos that there are 3 types of quarks. So you've got your up quarks and your down quarks and your strange quarks. And we've seen that the strong nuclear force basically only acts on quarks as well. So that was in a previous video. So the next piece of information is that when we're looking at the strong nuclear force, strangeness is always conserved. So whenever you've got a strong interaction, strangeness is always conserved. So however many strange quarks you start off with, that's how many strange quarks you finish with. So for example, if we take this thing here, we could, for example, do this. If we basically hit an antiproton and a proton together, we could, for example, make a K plus and a K minus meson, like that. Now if we look at all of our baryon numbers and charge and lepton numbers, then this equation is absolutely fine. But beforehand we had no strange quarks, because obviously this thing, the proton has got quarks of up, up, down, antiproton has got anti-quarks, anti-up, anti-up, anti-down, but it's created some strange quarks, but it's created them in such a way that the strangeness in this interaction is still conserved, because a K plus has got that quark structure, and the K minus, oops, sorry, there shouldn't be a minus one, the K minus has got this. So overall, this has got a strangeness of -1, this has got a strangeness of +1, this has got a strangeness of 0, and so has this. So strangeness is still conserved, and that's why kaons, when they're created via the strong interaction, and they're only created via the strong interaction, so that's really, really important there. That's why kaons are always created in pairs, because they're created so that the strong interaction conserves this strangeness. So you could start off with no strangeness, finish up with no strangeness altogether, but because you've created essentially a particle and an antiparticle with strange quarks in it, then the strangeness is still conserved. Now you can use this to answer other types of questions. So for example, this is one of the more difficult kind of A-level questions that you could potentially get. So here we've got a kaon that's already been created in another interaction, and it's going to interact with this proton here. And when it does that, it's going to create basically 2 more kaons and a particle that we don't know. And what we really want to know is we want to know the quark structure of this particular thing. So we want to know, ideally, is it a baryon or is it a meson? Because we're told it's got a quark structure, so it must be one of those 2 things. And then once we've worked that out, actually what quarks is it made up of? So what we would do is we would use our conservation laws. So the very first one I'm going to use is charge. So we'll just look at this. So this is a K minus, so this has got a charge of -1. This is a proton, which has got a charge of +1. And that's gone to this thing, so it's got a charge of 0, plus a charge of so that's a plus K-on, so that's got a charge of +1. So this thing, if we look, this thing must have a charge of -1. And the reason it must have that is because if we look at what we started off with here, we've got -1 plus 1. So the overall charge was 0. So we need to finish up with an overall charge of 0. So that had a +1 charge, so this must be -1. So our X meson, our X particle, whatever it is, has got a charge which is equal to -1. Now that's not really going to help us in terms of what quark structure it's got, but it will give us a check towards the end. So I'm going to have a look at baryon number now, because the baryon number should hopefully tell us whether or not this thing is a baryon or whether it's a meson. So this is a K meson, so the baryon number of that is 0, plus a proton. Well, protons are baryons, so that's got a baryon number of +1. That's gone to a K0 meson, so that's got a baryon number of 0, plus a K plus meson, so that's got a baryon number of 0, plus, well, we started off with a baryon number of 1 altogether, so we need to finish up with a baryon number of 1 altogether, so this must be a 1. So therefore our baryon number for this particle is 1. So we automatically know now that because it's a baryon, it's not an antibaryon, it's a normal baryon that's going to have a quark structure of quark, quark, quark. So we know it's got 3 quarks in it. Now what we need to do is we need to try and identify what these quarks are. Now, the way we're going to do that is I'm going to use my strangeness. Now, this is where this part becomes really important, because I know, and I would underline this if I was doing an exam question, I know, for example, that the strong force always conserves strangeness. So that, as soon as I see that, I know this. So whatever strangeness I've got on this side, I again will finish up on this side. So let's have a look at this. Well, this is a K minus meson. Okay, so if I remember my quark structure, this thing has got a strangeness quark in it, so therefore has a strangeness of -1. This is a proton. This is made of just up and down quarks, so this hasn't got any strangeness, so that's got a strangeness of 0. So altogether I've finished up with a strangeness of -1, or at least I've started off with a strangeness of -1 in total. So then I go to this. So a K0 has got an anti-strange quark in it, so that's got a strangeness of +1, plus a K plus particle. Well, that's also got an anti-strange quark in it, so that's got a +1 in it, so I've got a 2 so far, plus whatever this is, and I don't know what this is. But if I look at this thing as altogether, I started off with a strangeness of -1. I need to finish up here with a strangeness of -1, but I've got a +1 and a +1, so that makes 2. So this thing here, this X, must have a strangeness of -3. So that automatically tells me what the quark structure of my baryon is. Well, because I know that a strange quark has got a strangeness of -1. So the only way that I can get a strangeness of -3 is if I've got 3 of them. So in actual fact, the quark structure of this particular baryon here is a strange structure. If, for example, I had just got a strangeness of, for example, -1 here, then it would just have 1 strange quark in it. And then what I'd have to do is, if I know it's got 1 strange quark, I'd then have to use the charge using up and down quarks in order to make the correct charge. I don't really have to test that, because I know in this case that the charge of a strange quark is -1/3, and because I've got 3 of them, that adds up to -1, and so my charge actually works as well. But if I only had 1 strange quark, for example, I'd then have to combine my up and my down quark along with this strange quark to make the charge that I needed. So just to summarize very quickly, we've had a quick look at the strong nuclear force. It only acts between quarks, so it acts between individual quarks in terms of gluons, but then it keeps hadrons and baryons together by exchanging pi mesons. We had a look to see how it keeps the nucleus stable, and most of the time it does that because it's a stronger force than the electromagnetic force. But if your nucleus becomes too big, then basically the nucleus kind of falls apart and emits an alpha particle. So this is why you get alpha decay. We had a look at this graph, and we saw that it's got there's a short range attraction. In other words, between for example, two neutrons, If you're further away than about 3 femtometers, there's no force. If you are looking at separations between these two particles of less than 3 femtometers down to about half of a femtometer, you get attraction between these two particles. And if the separation between these two particles is really, really small, below about half a femtometer, then this thing becomes repulsive, and so they feel repulsive force and would move away from each other. I explained that you need to be able to do just the same as at GCSE, that you need to be able to complete these types of equations, and you have to remember these numbers. And we saw that strangeness is conserved, and you can use that basically to help decide the quark structure of unknown particles. And again, importantly, kaons are created in strong force. I'll get rid of that. So kaons are created in the strong interaction, and they're always created in pairs. And the reason for that is because strangeness is conserved. So I'd like to say thank you very, very much for watching, and I will see you again soon.